synchronization is screens in front of you, left and right, behind you, around. It's 24,000 pixels and more. And the ceiling has the same resolution as everything else. It's an insane place. If you haven't been there, you expect a lot, but it's bigger. And that's only one of many locations in this building. There is this is again the big room, but there's also a smaller version with only 3 walls, like ceiling and 2 walls. This is called trending. And then there is the arcade. This is a long way. You can't see here. If people are in there, this is like 4 meters high. And it's LEDs all around you. And outside, of course, you got even more LEDs to show whatever advertisers want to be shown. And there are more screens all over the place where you just have timetables and that kind of stuff. Our part as Ventuz was to develop the software that drives all these screens. And let's talk a little bit about Ventuz. Ventuz is a software company located in Hamburg. We are doing this for 20 years now. I am there for 12 years. Also, KB of Farbrausch works there. BoyC from Conspiracy works there. This is a scene-friendly environment. Pretty much everybody there knows what the demo scene is and has seen demos and likes that shit, like we do. And we do all kinds of interactive graphics for everything. And here's a little show reel of some things we did. There should be sound.
There should be sound.
There should be sound. There was sound during the rehearsal. Showreels are always cut so fast you can't see anything anyway. So this is our big screen, actual size, actually really big. Ventuz drives all these coordination of all the videos that are played out there and interacts with the software that schedules and controls all the advertisement, because all this data-driven interaction is one of the strong points in Ventuz. Next. There is, this are images from an agency that works a lot with Ventuz. This is all done with Ventuz, doing like interactive environments where you can do fancy stuff. Yeah, this is done by Inti. And this is not supposed to have sound? No more sound. No more sound. But not everything that is real-time needs that you interact with sensors. Broadcast graphic must be interactive, so the director can press a button to bring stuff on screen immediately, or to update the latest score of the game. So you unlike wrestling, you don't know what's happening, so here has to be real-time. You can't prepare for all the situations that come up. And this was a real broadcast graphics that we were allowed to rebrand to use for our demo scenes at exhibitions and stuff. Maybe you can guess who that was. Another thing, this is from the League of Legends studio in Berlin. They also have 2 other studios. The studios run all with Ventuz. All the screens you see on the studio are controlled with Ventuz, and in the Berlin studio also all the broadcast graphics that are streamed out go through Ventuz for all the branding and interactive graphics on top of it with all the stats from the players and whatever. We even got camera-tracked virtual things done with Ventuz in this studio. Yeah. The Ventuz is a node-based system. This is very much like a demo tool, but some of the ideas behind this are still unique after 20 years. All graphical programming tools have the problem that the graphical hierarchy or network can only display one aspect of the system. In Ventuz, the same node can appear in two different views. One is a scene graph hierarchy, and the other one is where we bind all the logical elements together. And you see the one node that is highlighted in orange, that's the same node appearing in two different graphical contexts. And as soon as you understand this, because it's a bit of a mind wrapper, what Ventuz is doing there, you can keep stuff organized. You would not be able to organize in any other system because you're not bound to one way of arranging your nodes. You have these two different views for two different reasons. Yeah, the scene graph is not a standard scene graph. It cannot only transform things in 3D. It also holds other information like colors, material elements, and all other stuff that makes sense to put in a hierarchical scene. So you can add a texture node. You see the red thing there is a color node. And everything behind that color node will be red. And you can add a texture. And everything behind that texture will have that texture applied. And all the shaders are automatically integrating that texture that you put into that hierarchy thing. These are, and another thing that does Ventuz exceptionally well is the state machines. You can build state machines that interact with all the graphical properties that you can have in the scene. I think it's pretty much unique how that is dealt. And the ability to create state machines and complex logic allows you to create these interactive scenes with quite some fidelity, if you know what you're doing. It's impossible to summarize everything that Ventuz does because it does so much and it is used in so many areas. But when it comes to graphics, logic, and I/O, when these three elements come together, Ventuz is in the game. And when you then need to scale to large clusters, it's sometimes the only thing that will actually work for you. In general, Ventuz develops the software, and then agencies and freelancers do all the integration for some end customer. But occasionally, we do special projects. We work together directly with these end customers from beginning planning and later until on-site until it's done. These projects challenge our software to grow, and that's why we get involved closer. And exactly that, this is spoiler alert, the team that does all that integration, that customer cooperation is looking for people. Ventuz isn't only looking for programmers. We also look for graphics-oriented, use-oriented people who use the software in-house, to learn the software, use the software in-house, and then go out in the world and tell our customers how it's done. But more about that later. And before we can go to Outernet London, which you're all waiting, we want to show the special project where we didn't have the software that we developed. It's the project that inspired us to break what was, to go beyond what was formerly possible in Ventuz. And that's the Nook.
Nook. Hi, yeah, my name is Dennis.
Microphone?
I don't know. Hello, hello. It was working beforehand. Anyway, I can talk loud enough. Yeah, but is it working? Yeah, okay, cool. Yeah, my name is Dennis. I'm working with Ventuz for about 10 years. I'm in the product support and software development team. So my job is most times to go on site or create very close with the work very close together with the development. So I can bring in ideas and the developers or the coders try to put that on the roadmap and yeah, fulfill the requirements.
Microphone is working.
Yeah, looks like. We had several years ago the project called Nook. It's a Northwestern University in Qatar. And they created a museum for all the college students and also for the public. And this one was made out of a huge armature steel construction where they had several screens attached to. They had several touch kiosks where you can get information about, I don't know, any kind of topic which they want to exhibit there. And this was quite interesting because we had this huge armature, we had these touchscreen kiosks, separate ones, we had this one big video wall, which is also interactive. They had LED ribbons or infrared ribbons on top and the bottom, so it recognizes the touch informations. And we had two more video walls, one at the entrance and one at the center. So let me show you that. What you see here is the top view. This is the armature there. Behind the armature are also some screens. Then we had this curve where they had these kind of touch screens, the single touch screens. Here's the entrance area with, I don't know exactly, it was 3x2 screens. And then we had the huge video wall here on the right-hand side, which you've seen in the last picture beforehand. So everything in this case was driven by, in total, 42 machines. It was driven by another software solution beforehand, so all the stuff was already fixed, especially the screens, the cabling, and all these things, and that was a big challenge for us. So this is the technical view of the armature, just a part of. This is a 4x4 case screen, which is in the upper left area, which is very tight together, and the screens are seamless, it's fine. So when you have such an installation, it's quite easy to address or map everything onto the screens. You have like no gap between, that's fine. But as you can see here at the armature, we had several screens distributed all over, and this is not enough. We had screens with an aspect ratio of 84:8, sometimes even more strange. And these had, as you see here, this purplish one, for example, is one of the craziest I ever had. And this one is full HD. That means 1920 by 1080 pixels, but in that kind of strange aspect. So yes, never seen that before, but they bought everything you can get on the market, yeah, and they want to have it, yeah, like an artistic installation. Yeah, and Ventuz has had at this time issues with having different aspect ratios, different kind of resolutions per screen, because basically we're using mosaic or affinity setups. So that means when you're using these and have a huge, big Windows desktop, you cannot have a single screen in the middle which has a complete different resolution. That doesn't work out. So everything is the same size. What you see here is the render setup for that. Yeah. So these gray borders, which you see here, the light gray borders, are the borders of the machines. So this is one single machine containing this small screens inside. These are the outputs in the end. And as you see, it matches roughly the armature we had seen there before. This orange border, what you see here now, I zoom in into this armature, into the render setup, and this orange border you see here is one machine. But notice we have the light gray, another machine, inside of it. Why? Because this screen, this one, and that one to that gray bordered machine, and the rest of the screens you see in here, this, and that far away belong to the other machine. So we had an overlapping of the content in the end, because the architects decided to have that one screen here in the corner connected to the machine which usually drives the one on the right-hand side. So this is total madness. And it was not possible for us to change it at all, yeah, because cabling was done. You could physically just inter-exchange between the 6 outputs on one of the machines, but we could not use that one cable and throw it over to the other machine at the end of the CER. It was not possible, simply not possible. Aside from they used fiber optic cables going from the CER 340 meter underground into the exhibition, into the museum. It was a mess, believe me. One cable being broken, and they had to drill new holes through the whole cellar area to get one cable back there. It was hilarious. So, but this kind of things happens, as you know. So what you see here is, again, the technical drawing on top and the render setup on the bottom. You realize it nearly matches already what we have created in the render setup, yeah? So you had to distribute that. This is the total resolution we've been rendering for the whole thing. The bad thing is you have, therefore, these gaps, massive amount of gaps between, as you see. I just pointed out some of them. And all of these full HD, even the small screens full HD, even the ones that had the strange aspect ratio full HD, and that's the reason why we had just matching rectangular 60 by 9 matching screens here in the render setup. So that's also a reason why they overlap here a bit. Yeah? So keep in mind, having these gaps creates another waste, and the waste is, in this case, pixel waste. The red marked area is the rendering area. This is where the whole content being rendered internally on the machines. The code, the blue area, is the one that we never ever use. But we had to render this height because here you see there are some screens that need some pixels in the right-hand bottom area. The yellow ones are actually the screens. So if you would put them all together, you have like 75, I don't know how much percent, I want to calculate that, by the way. You have a lot of wasted pixel, wasted performance in the end. So this will not work out. Another waste we had in this case was the touch screens, these touch kiosks, these eight screens we had there. Each of these touch screens needed one huge, big computer with just one GPU output. What a waste of money, what a waste of machine, what a waste of energy, if you want to name it these days. So it's hilarious what's going on there. One thing that was good was we didn't have to do the technical setup. It took me on site 2 weeks to set up the machines, configurations, network configurations, done the interfaces, applying the render setups. Someone screwed up the render setup because he decided to go on with a laptop, connect to that network, using the Ventuz configuration editor, and just grabbing out some machines and playing around, hitting save, and it was like machines disappearing, render setups were changing on site. What's going on here? Am I crazy? And I figured, oh yeah, man, it was the first time I can touch Ventuz, and I just figured I can play around with it. I say it on a live site, on a live installation. Thank you. Another good thing was we didn't have to create the content for it. It's a nice installation. It's also visually very, very interesting. It's completely different to just a simple video wall and square and such. And I was happy to have not to create the content because you had the backends, you had CMS, you have everything in the background to drive and run these events and installations. And that's why we had this.
We decided to, this is not good enough, we need to improve it. The main problem was that we had too many machines. That's way too many machines to create the number of screens. We wanted, for instance, to connect 4 touch screens to one machine. We want multi-GPU, multi-output per GPU, multi-SDI, multi-camera tracking, and multi-touch. And so I started on a project that I called Multi-Multi that officially became Ventuz 7. And we start with the box. So how many GPUs can you cram in a reasonably sized CPU case? And I really want to have 4. But unfortunately, you don't only need the 4 GPUs, you also need that sync board down there that makes sure that all the GPUs have their vertical blanking in exactly the same millisecond. We also need an SDI board because for video input capture stuff. So we can only, in a standard case, we can only cram 3 GPUs, a sync board, and an SDI board. We didn't want to create our own case. That just would have been a complete nightmare for a company of our size. But this we can reliably make and ship. We also need an AMD EPIC CPU because they have tons of PCI Express to have for the GPUs, for the SDI, and for the storage that is connected to it. And this little thing here, that is the sync board connector. That makes sure that your GPU flips in exactly the right moment. This connector changes a $2,000 gamer card into a $7,000 professional GPU. Also, there's more RAM, but it's basically, if I can't have this connector, I can't use it. It's garbage in a big setup. And that's worth $5,000 yeah. There's no choice. So you would take a sync generator that generates all these sync impulses, and they go through coaxial cables to all those sync boards. The sync boards are inside the computer, and the sync board is connected to each GPU, and then everything works. Sync boards are very simple hardware. There's just a very cheap FPGA on it. They still cost $1,000. Thank you, NVIDIA. In a TV studio or in any big installation, you will have something called the house sync, and that signal will keep everything in frame with even the fucking electricity. The sync board doesn't even connect to the SDI bus. So when you saw it hanging outside of the box in the image at the start, that works. You only need to, it doesn't need SDI, it just connects to the video cards and needs some power from a SATA cable, and then it works. But still, we wouldn't ship that. That was a little bit too flimsy. This is an SDI board. SDI is serial digital interface. That is the standard for professional video. A simple coaxial cable will carry 60 Hertz HD over 100 meters. Try that with HDMI. Or 60 Hertz 4K over 40 meters. That's still okay. You need this SDI. You need the SDI to get in and out of the PC. So this board will put it on your PCI Express, and then you have to copy it somehow over PCI Express to your GPU where you need it. That's a little bit nasty, but well, that's it. Yeah, so this is the box we designed. What we can do to make sure that we don't need so many boxes. We worked together with specialized PC builders who did help us select the hardware components. So this all will work for 24/7 reliability, and also we don't have to wake up at night because one of our machines broke. They will take care of that. They are in that business. So we have decided for the hardware, and the next is the software. Usually, when you have one machine with many outputs, usually you would use the NVIDIA control panel or the AMD control panel, but AMD don't have sync connectors anymore, so forget AMD. You would use the NVIDIA control panel and set up Mosaic to combine all the outputs to a single large surface. And I cannot explain in words how much that sucks. The software is total crap. Setting this up for one machine is bad enough. Doing a cluster and your day is gone. This is unexplainable, but this is what you get if you pay those extra $5,000 per GPU. It's insane. So we decided that we don't need that anymore. We control each output from each individual GPU individually. We don't have to set up Mosaic. You don't have to set up Eyefinity. Thanks to Windows full screen optimization, there isn't even flickering when you start Ventuz. It just works. Everything's there, plop. And that was, for many, many customers, like the biggest relief. We have to use Ventuz 7 because we don't have to deal with this shit anymore. Yeah. So each GPU renders its own portion. Here we see like we have 3 GPUs and 9 outputs, and we divided things wonderfully. But as you might guess, this is a really bad split because the GPU in the middle is now doing way too much work. So you should better split it in like this way. And now all the GPUs have a reasonable amount of work and everyone's happy. But obviously, that doesn't always work. Sometimes you get content that's just bad and, well, what can you do? It sucks. But that's how it is. Also, you might want to avoid these L-shaped things because then you can imagine how your GPU has to render all that black area. You can mask it out, but better not have that than to have to deal with it later. You stay here. You would want each GPU to render as few rectangles as possible. So when you are rendering on some of the screens things from one perspective, and on other screens things from another perspective, like in that giant room at Outernet, you would want to have each wall their separate machines so that the CPU doesn't have to deal with multiple viewports. At least not to deal with multiple viewports per GPU, because that's all work that has to be sent to the GPU from the CPU. So also, when you have live inputs, we support 4 times 4K inputs. If you want to distribute 4 times 4K to 3 GPUs, that's 4 times 3 times 4K at 60 Hertz. That's a lot of bandwidth. Epic CPUs have enough bandwidth to actually do this, but again, it's a lot better if you don't have to deal with that shit and plan ahead your setup that you can say this live video input will only be used by that video, or video decode's the same. This video decode will only be used by that GPU. If it's done on the CPU, you have to move the data across. If it's done on GPU, you have to use GPU resources to compute it. This planning of what's put where is very important, and there are all little bit masks that you can twiddle with so that GPUs don't see stuff they don't need to see. Like when you are doing stuff in the 3D space, it's not always clear what data is needed on what GPU because it's all transformed and shifted around. Yeah. Another picture. We have the SDI. Yeah, the SDI boards are also, this one, sorry, I got a little bit. If you render things on GPUs, and every GPU renders their own image, you see a little gap in between these things, because if somebody blurs something, there's nothing to blur it in. So you have to render stuff a little bit bigger than you actually need, so there's some meat to draw in for these blur effects between the GPUs. And now we come to the sync test. We know the sync board will take care of all these inputs, of all the outputs being absolutely in sync with the vertical blank in the whole house. But that doesn't mean that your images actually come out in the right order, because you have all kinds of buffering in between. You have the rendered frame buffers in a flip swap chain. You have unrendered rendering commands queuing up in the command buffer. You have uncompressed videos and compressed videos queuing up in the video coder decoder thing. So there must be software, and that's basically my work, that monitors the state of all these queues and makes sure that everything is buffered up the right way. So when it comes out of the display port, it's actually the right frame that comes out there. So all these buffers need to be monitored. And it is impossible to make a system that never drops a frame. This is still a Windows machine, and Windows might decide it's a good time to scan for viruses or whatever they do. And then you drop a frame. So the important thing is once you've dropped a frame on one machine in this giant wall, that this is recovered quickly and smoothly and reliable. Because if just one machine hangs and keeps hanging, everything is ruined. So one of the things you can see here is the face display, where we monitor exactly the face on when things go out. The two aligned ones here, Those are the exact timing of when the image is sent out of the display port. The one that's a little bit off is the network cluster impulse that synchronizes the cluster across each other. It only has to be correct for one frame because we know our V-blank will be absolute rock solid. That's hardware guarantee. So we have like 60 milliseconds for the network to do it. That's easy. Yeah, and there's enormous amount of testing, looking at stats, looking at flickering bars, and having these systems run for 24 hours, the whole weekend with 3,000 watts of power coming out of the back. Very nice to warm your hands in a cold winter night. But eventually, yeah, we got that going. With video projection, the old style, you have two projectors, they overlap. You can hide some mistakes in the overlap. There's like a larger area than you might think where things overlap. And if something's a little bit off, doesn't matter that much. But nowadays, we have LED walls everywhere, which are perfectly next to each other. Even the untrained eye will see the slightest of that here. You can't fool us demo sceners, but you can get away with a lot. But nowadays, with these LED walls, you cannot get away with anything. Everyone sees this is not correct. And remember the scale of things. The big room is 7 machines with 21 GPUs, one unused, 20 GPUs maybe. And the whole building has 17 computers with 51 GPUs, plus a few test systems. Imagine we had 51 GPUs. Things never run smooth. There's always something you need to tweak on each machine manually, multiple times. Dealing with 17 machines is already a lot. So cutting this down by a factor of 3 is a great relief. And that's me, sitting in Hamburg, playing with my computers, writing cool software that actually somebody needed, which was good. And now come you.
Finally we come to the Outernet in London. So this was a real ride to get the software developed to the stage where we could say, okay, it's not only a proof of concept, it's working and we can go to Outernet and install all the machines. So this was also my job and the job of 3 more colleagues of mine going over there. Let's get an overview of the location. This is the Outernet in London. It's nearby the Denmark Street, a very famous street several years ago when we basically been born at these times. For the musicians, a very, very famous area. So what we have here is the Outernet. This one is the biggest venue. This is the Now, the so-called the Now. This one has a height of, I don't know, is it like? I thought it was 40 meter high, but maybe it's only 40 meter wide, but it's massive. Yeah, it's massive, guys. Believe me, it's massive. Then we have the trending. It's basically the same thing like the Now, just not that high. It's like we said 3-4 meters. You could barely touch the ceiling, so it's like 3 meters apparently. We have so-called pop areas. These are areas for product presentations, for product placement. And then we have the arcade here in the middle, which is a long gangway, like 10 meters long, high ceilings, and so on and so forth. We will concentrate here now on the Now, this biggest one. When you arrive there, this is how it looks like. You see line arrays here, and for the most of you, I think you can scale the size of a line array compared to these walls. It's amazing. And at first it looks like a cube, right? So, but in fact it's not. When we have an overview, the top plan of it, you realize that we have just 2 right angles, the one here in the top, and the one here on the left-hand side, but it's more like a kind of trapezoid. So it's for the mapping, for the creative guys later on, it's a kind of limitation, which we'll come to later. So this is not that easy to create content for that. From outside, we have even more screens, as Dirk mentioned already. This is the Vista, and this is kind of really an amazing thing. So you have seen the inside, yeah? So you realize that that a kind of amount of screens is also on the outside. What they can do is open up this window blinds, so in good weather condition, they keep that open, and also they can open up these walls. These are cabinets, like, I don't know, 60 centimeters in the width or something more, and these cabinets can be put behind the other walls to open up the venue for the outside. This is done in minutes. I'm not talking about 10 minutes or something, like minutes, 7 minutes, and all these cabinets go open and go behind. Closing is the same, and they have no sensors. So if there is a pigeon in between, it's a flat pigeon. It's 2D, yeah? So this is kind of really strange on one hand. And keep in mind, one of these cabinet rows is about 3 tons. It's massive. It's really massive, believe me. This is a kind of inside view, a very, very crappy one. I just took it with an old mobile phone. And these are the 5 walls we have there. We have the east wall, we have a south wall called Hero, because this is the most prominent wall. When you get inside of this building, this is the biggest wall we have there. Then we have the west wall, the north wall, and the ceiling. These names became very common for us. As I arrived at London, it was in an early construction stage, as you see here. So we put our test pattern on it, which is the testing mapping pattern. It has several informations on it. And the guys from our auto, which were the guys who were mounting all these LED panels, are also responsible for the mapping. So they need to map their controllers matching to these tiles, to each 64 by 64 pixel tile. Seriously, this is absolutely stunning. Look at here. You see, there should be an A. It's completely twisted around. There you see the 64 by 64 panel. So they had sometimes to go upstairs, change the mappings. During installation of these panels, the whole building being under construction, you had some dust falling on top of these panels. These connectors are also very sensitive. They break down while they've been mounting that, going again up with a cherry picker, remounted, and so on and so forth. The whole process took weeks, believe me, day and night shift, 24/7 they've been working there. Here you see, right-hand side, the inside panels not being installed. Cherry picker all over the place, while the ground floor was already done. So this is, like I said, the hero wall. We will now concentrate just on this hero wall for the moment, and I will show you how we did it and how we made it. The most important thing is, this is really in the designer, here in my Ventuz designer, when I light up just one single pixel, this one single pixel will light up in this installation. It is not like it is usually common that you have one machine rendering something out using an FX4 controller and scale the thing up to a 4K wall or something like that, where you have blurred pixels, in fact, because they've been scaled up. This is really driving 1 pixel by 1 pixel. Since I had the architectural plans for that, I could also see these simple panels, and the same goes for the ceiling. You see the blue, dark bluish areas here. This means this is just like a half array of the 64 or 60 panels. These are not full panels, and so on and so forth. And I also had the rigging points inside of this plan. So I created a scene for them based on these plans and light up where the rigging points are in the ceiling, so they could easily and quickly go with a cherry picker, unmounting a 64 by 64 pixel panel, having their rigging point there, hang up something on the roof, on the ceiling. This was so welcome because the one guy was running crazy saying, how should I know where is the rigging point now? I said, simple idea, just use my scene. And they were pulsing. And he was like, if that matches up, I'm gonna kiss you. I avoided that because this was during the COVID times. So, but nice offer. So, yeah, he found exactly the rigging points. He was so amazed, happy. So how does it work? We have a Ventuz scene. I said we concentrate on the hero, yeah? The hero one is this light red area. This is the whole scene that we created or that they can use for their content they want to bring out on the walls. This one wall is driven by 2 machines with total of 6 outputs. These GPUs, each GPU has just one 4K connector. This one connector goes to the Aquilon. Aquilon is taking all the input and has some kind of layers available where they can map the stuff which comes from Ventuz and distributes this over to our Auto. Our Auto are the display controllers, and then they have to really map this stuff from Aquilon onto each separate panel. So the output in the end is like for the hero wall, this so-called S1, S2, A3, A4 output. These are 4 layers inside of Aquilon. Doesn't matter for us. We will come to the color coding which you see here later on as well. It's important. This is now the render setup for this one wall. It's way easier than we have had beforehand in Nook. So this is just the left-hand side of this hero wall. I can compare it to the wall. This is the wall hero wall. 3 outputs, 1 machine, 3 outputs, second machine. Yeah, just to give you a hint how it works. So I colorized these 3 outputs you see here. So the Ventuz scene can be prepared, and we just use and cut out areas of this Ventuz scene, really calculated pixels. Yeah, you can calculate how many pixels we need for that part, and so on and so forth. And then you take this output. This is the output mapping. That means I grab something from this part of the wall and distribute that on this 4K output for the output. That means this part here. Then we have the both bottom parts, which you put on the right-hand side. So we can use as much space as possible. We can also rotate the contents there. It's just going to the output, and then it's taken by our Auto, or in this case by Aquilon, and they grab parts of that and put that out. So here we have 1, 2, 3 GPUs, these red, green, and bluish color going in here, and then we see it on the walls and the big output. Remember the colors, 3 GPU outputs, red, green, blue. This is the red part of the video wall. This is the green part of the video wall. And here, in the lower part, we have the blue part of the video wall. This is the one machine delivering the content for the video wall. We can say left, the one machine, right, the other machine, basically. So Dirk's amazingly fucking job was to synchronize between these both machines when we have SDI input, when we have playing back a movie, when we have 3D content going over in real time, whatever, yeah, because we have a machine border. We don't only have the GPU borders, we have the machine borders. That means GPUs needs to be synchronized, then these 3 GPUs needs to be synchronized with the secondary machine. This is a hell lot of fucking work, believe me. This is absolutely amazing what he did there. Again, this puzzling. Then, after a week, we came to that. And there you see again the S1 and the S2 reflected in a real huge manner. Believe me, 1 pixel could be lit. It's not like blurred, it's not upscaled. It's amazing. Here you see again the architecture visualization represented in certain colors for a reason, because you need to tell the content guys, the artists more or less, how they can use these video walls. So we had to come up with 3 different mappings. This is the first mapping we have, but there is a limitation. You can go horizontal-wise, you can put content in here and move it over seamlessly, no problem. You could go from the hero wall to the ceiling, no problem. It will wrap correctly. Everything, text and so on, will float and look correct. But if I would shift the text to the left-hand side, they expected to have it then appear on the left-hand mapping on the green one. This is right now not possible to have it jump from here to there. It's not possible. So we need to deliver a second mapping solution for them, which we call the ceiling mapping, because everything is concentrated from the ceiling and can then go to the right, to the left, to the hero, to the north wall, wherever it wants to, but cannot go around. So they had two different mappings already, which they can make use of. The good thing is we have several layers available in Ventuz where you can blend between those. Either you use a completely different mapping between and blend from the hero mapping to something that you use as a transition layer, and then to the other mapping. This is easy for them. All at once. So you have freedom, which is unbelievable. The third mapping I was mentioning is the point of view. So that means you can have a spherical mapping around that. Yeah, you can stand in the center. This is common, which you know from Japan or wherever else, where you can stand at the street at a given point, looking at the LED installation in the corner. It looks like all the content is real 3D and pops out. Yeah, like Back to the Future, but a bit more 2D. So this is possible there as well, but this is not common to be used when you want to have product placement, two-dimensional images or whatever. You cannot fix them on the screens. Yeah, in this case it's not possible. So you can have only one of these mappings available in the end. This one was for the UNICEF Gala, and believe me, when you stand in there and you see this moon rising or moving around in the now, in that high resolution, it's quite impressive. So everything counts on the content available from the content creators, and they have a lot of freedom to do so, quality-wise as well.
That's the hall you were just talking about?
Yep. No, that's the same installation. It's just the hero wall. It's just a picture from the hero wall. Yeah, obviously, that was London, Outernet. We are hiring. My job was to be on site there. It's absolutely stunning to work with these projects. This is not the only big one I have made. I've done also with my colleagues together. The good thing at Ventuz is I am working, and all my colleagues are working very close to the developers. It's not like that I'm focused on a special thing. I'm also a creative guy, like I said, more than 30 years I'm doing graphics, 2D and 3D graphics. I had a lot of ideas. I'm also sometimes in the Elite House where Farbrausch is meeting up and other guys. And as you know, we all have crazy ideas and we want to bring them to life, and Ventuz is absolutely open for that. And that's fantastic, that's brilliant. My boss is also very, very nice when it comes to such ideas, great ideas. It's not like we have a cigarette outside or something like that and he's like, yeah, thank you. No. He really thinks about all these ideas and features everybody in the company comes up with. This ideas brings just the software forward, I would say. Thank you, this is just a rough overview. We don't have enough time to really go into detail. I can tell you stories about the Outernet, you won't believe me. Having pictures and such. So if you want to get in touch with us, just talk to us. If you have more questions or whatever, just get in touch with us. We can now do a quick Q&A if you want to.
We are supposed to get a microphone.
Yeah, and I will shut down mine.
Yeah, just ask. Maybe I keep this one on. Yeah.
Website. Okay, thank you. I had a look on your website, and there's notch integration, and your product seems to be in a sort of a similar market. So I'm curious how that works. And second of all, I work at Maxon, and I saw that there's C4D integration. I didn't hear about that, so I'm also very curious how that works. If you have a second.
Yeah, one part of Ventuz is that we integrate with all kinds of things, because with Ventuz, you're not stuck to this thing. We have an Unreal integration. We have a Maxon as data to get data inside Ventuz. You can have Blender to get data inside Ventuz, standard formats. We are very open to this. Thing is, Notch is a plug-in. It does not provide all the interfacing to the outside. Of course, it always works better if you use the integrated engine that Ventuz already has. But if you think you have a problem and you need to use another engine, that can be integrated. In many cases, it's some marketing people who said, but you must have Unreal, otherwise we are not buying this. And then they figure out they could make their life much more easier if they were just using Ventuz in the first place, because Unreal. Thank you. One more thing, I have to be going very soon over there to the business forum, where I will be highlighting the fact that we are looking for people, and we are looking especially for people who are not coders. We are also looking for coders, but if you are not a coder, but you are a talented guy at working with graphic software, with 2D, with 3D, you might be exactly what we are looking for, I mean, and at maybe. So to clarify that, and another question, please.
Yeah. I'd noticed lately, browsing Twitter, that animator Mr. Weeble had been considering, well, wishing that one day he could get his virtual pop side project off the ground in some capacity. So could this be used, this system be used for like a virtual pop star or a virtual pop band or the like? You know, sort of Pepper's Ghost kind of thing?
So like a V-idol thing?
Yeah, possibly.
We have never tried this. And I believe in putting that off, certain standards must be implemented, and I'm not sure if we currently implement all the standards you would need for that to integrate with the controllers you have to puppeteer this thing. There's for sure something we don't yet support, but there's always the C# node that allows you to integrate any DLL that will not crash the system, to grab data and push that data into the Ventuz thing, which will then have GLTF character animation rigging that you can puppeteer. I can imagine that hooking up the matrices will be a pain in the ass, but I don't know how the V-idol guys do that normally. Specifically, all the I/O, the video in, video out, streaming, all that stuff, it's all there. It's very comprehensive. So if you can get the DLLs you need to do the stuff that's not possible with an off-the-shelf 3D engine, then you should be fine.
Cool. Thank you, guys.